We know that light waves consist of electric and magnetic fields that are vibrating in directions that are perpendicular to each other and perpendicular to the direction of travel. So for example, if we had an electric field that's vibrating up and down, that's the easy one to draw, and the wave is traveling in the direction to the right, the electric field is vibrating in and out of the plane of the board. I'm going to try to draw that. If you can kind of see what I'm doing here. It's vibrating horizontally. So this would be the magnetic field and the electric field. But usually when we have light, not all the light is vibrating, so that the electric field's vibrating in one plane, for example, up and down, and all the magnetic fields vibrating in the perpendicular plane, for example, side to side, horizontal. Usually when we see light, for example, coming from a lamp or the sun, there's some parts that are traveling, have the electric field up and down, some have the electric field side to side, and some have it at random diagonal angles. We call that unpolarized light. That's most of what we see in our daily lives. There are polarizing filters. For example, a lot of sunglasses cut out the horizontally polarized light because that cuts out a lot of the glare that we see. It's a filter, it's a surface with long polymer molecules, I believe, that are lined up parallel to each other, sort of like a picket fence. So you can think of it as these long parallel molecules, like a picket fence, and they let light through only if the electric field is vibrating along the axis. If it's vibrating, so light that's parallel to the axis gets through, light that's polarized perpendicular doesn't get through. So when you have unpolarized light that's vibrating in all directions, all of the one light that happens to be perfectly aligned with the polarizer gets through. None of the light that's perpendicular to the polarizer gets through, and part of the light that's at other angles gets through. When we look at the total that gets through, the intensity through the polarizer is half of the intensity of light coming into the polarizer. Also, the light coming out of the polarizer is going to be just polarized up and down. If polarized light travels through a filter, say you have a filter that's oriented up and down, like in the last slide. Ooh, that's not good. Let's make these more parallel. And you have light that comes in aligned with the polarization axis, like I said before. All of that's going to be transmitted. If you have light that's perpendicular, none of that gets transmitted. If you have light that's at an angle, part of that's going to be transmitted, and it depends on the angle. I'll call that theta. So the intensity that gets transmitted is equal to the incident intensity, that's of polarized light, times cosine of the angle between the polarization axis and the light. So we've got one example here. Unpolarized light is transmitted through a series of two Polaroids with their axes separated by 45 degrees. What fraction of the incident intensity is transmitted? So the first step, we start with unpolarized light being transmitted through a polarizing filter. And from the last slide, we know, we'll call this I1. We'll say through the first filter. If you can read that, the intensity, I'll call it I1, is 1/2 of the incident intensity. Oh, let's change colors. Through the second filter, I'll say through second filter. I'll say I2 is going to be I1. It's I2, I1. I1 is the intensity that got through the first filter times cosine of theta. But I1 is 1/2 I naught. So this is 1/2 I naught cosine theta. So, or I'll write it down here. That's 1/2 cosine of 45 degrees times I naught, which, if I plug in those numbers, I get 0.35 I naught. Or I could say, I don't have room, 35, I'll say, % transmission.